Okay, let's look at this 2015 paper. Quite a typical question you tend to get. First one is, show that the product of capacitance and resistance has the SI unit the second. So if you remember, that product is our time constant, so it should be measured in seconds. And the equations we start with are Q equals CV, um, Q equals IT. So there's one mark for getting the both of them. And then also V equals IR. Okay, so we can rearrange this equation to give us C equals Q over V. And we can rearrange this equation to give us R equals V divided by I. And if we put both of those into this equation, we get that the time constant will be Q over V multiplied by V over I, which is just those two V's cancel out, Q over I. But from this middle equation here, we can get that I equals Q divided by T. So that would equal Q all over Q divided by T. Now they cancel out and the T comes up to the top. So it is measured in time, and the base unit for time is seconds. Okay. Draw a diagram of a circuit from which the time constant of a resistor capacitor network can be determined. The capacitor is initially uncharged. Now the reason they're telling you that is you need to be able to charge the capacitor. Now let me draw out the one they have in the mark scheme. It's not the one I would use. So they have a switch that is connected to our capacitor. We then need that something to discharge through, so we have a little resistor, and then you need something that will measure either the current or the voltage across the resistor or the capacitor or through either of them. So they put the voltmeter here, which is fine, okay, because when it's discharging, all those things behave in the same manner. So we can use any of those equations that we've got. I equals I naught e to the minus lambda, or t divided by tau, or the one involving voltage. So it doesn't matter whether we use a voltmeter or an ammeter there. Now, how does this circuit work? Well, when we close this switch, that will charge up our capacitor until it reaches the same voltage as our supply. However, it will also put a current through the resistor. Now, as long as that resistor is high enough, I mean, it won't actually affect the capacitor, but I just don't like that as a circuit. It does work because eventually what we can do is we can charge up this capacitor to the supply voltage, and then we can open that switch, and then what will happen is the only path that's available to the capacitor is the kind of bottom half of the circuit, and it will then discharge through the resistor. I would prefer you to use the circuit that we normally use to draw this, even though it's slightly different to the mark scheme. I would use a double throw, a two-way switch. I just think it's a cleaner way of doing this. That's our circuit, okay? So when that switch is in the top position, it will charge the capacitor. Now notice in that top circuit, that one highlighted in blue, there's no resistor, so it will charge quite quickly. If we move the resistor up into the path that has the capacitor on it, it will charge slowly and discharge slowly, and that we don't tend to want that. So in this way, switch, throw into the upper position, the capacitor will charge almost instantly. Then we put it down to the bottom position, and the capacitor will discharge. Now we then either need to measure the current in that lower circuit, or we can measure the voltage across the resistor, or we could measure the voltage across the capacitor. Doesn't really matter, they'll all change in the same way, so any of those would work as your diagram. Describe how the circuit may be used to obtain results from which the time constant may be determined. So Firstly, charge the capacitor by moving the switch to the upper position, and then move the switch to the lower position, and record the voltage or current every 5 seconds, 10 seconds, depending how quickly it decreases, but maybe every 10 seconds. Okay, so record voltage and time. This is an experiment you should have done the first week back after Christmas. We weren't able to do it. We will probably try and do this when you're back in school if we're allowed to do experiments in. Okay. Explain how the results may be used analyzed graphically to obtain an accurate value for the time constant. It's up to yourselves what way you do this. I think you're probably better describing how you would draw a straight line graph, but they do give it in the mark scheme as plot a graph of voltage against time. Draw a smooth curve through your points. Find the time taken for the voltage to fall to 0.37, which is 1 over e, or e to the minus 1 of its initial value. And then this is the time constant. Now that's what the mark scheme says. I'd like to see some other things in there, to be honest. I'd like to see you saying that you'd repeat that and average it. So that you would do it starting from another value of voltage and finding how long that takes to get down to 0.37 of its value. But that's the 2 marks for drawing that curve and finding the time constant from it. I'd almost prefer you to say that you would find the natural logs of the voltage, and you plot a straight line graph against time. And if we start off with v equals v naught e to the minus t over tau, taking natural logs of both those sides, you should be able to see if we rearrange that a little bit. So that should be our time constant, plus natural log of v naught. We can compare that to y equals m x plus c, and therefore the gradient of that graph is equivalent to minus 1 over our time constant. Don't leave it like that. So if I was putting this in an answer, I'd say we can then find the time constant by finding the gradient, and tau will equal minus 1 over the gradient. Okay, so tell them how you find the thing you've been asked for, that time constant. Either of those methods would get full marks. Calculate the charge stored on a 300 microfarad capacitor when charged to a voltage of 600. So you do Q equals CV, you put in your values, Q equals C, which is 300, don't forget to by 10 to the minus 6, multiplied by the voltage 600, gives you a charge of 1.8 by 10 to the minus 1. Coulombs are 0.18 coulombs. Okay. It then says that the 300 microfarad charge capacitor is then connected to an uncharged capacitor of capacitance 500 microfarads, as shown below. The switch is then closed. Calculate the potential difference across the capacitors. So initially this would be 600 volts, but that voltage is going to decrease as the charge moves across to this capacitor. So the first thing we need to find the total capacitance. We've talked about this type of question before. The key thing to remember, well, there's a few key things. First thing, they are connected in parallel. So we add or find the total capacitance just by adding the separate capacitances, which gives us that it is 800 microfarads. The next thing we need to say is that charge is conserved. So although some of the charge from the first capacitor is going to move around to the second capacitor, the total charge on those two capacitors when they add them together is going to be the same as above, which was 0.18 coulombs. So we can then do Q equals CV, but using those total values, 0.18 equals 800 by 10 to the minus 6 times V. So V equals 0.18 divided by 800 by 10 to the minus 6. And that should give you a voltage of 225 volts. Okay. Like I say, that's a common question, but the two key things to remember are when they're connected like that, they're connected in parallel, and the charge is conserved. The voltage will decrease, the energy will decrease as well, because we lose energy as the current moves from one of the capacitors to another due to heating of the wires. So they're the key things to remember. Okay.